Hello there, and welcome to The Sleepy Scientist, the place where curiosity meets calm and wonder gently slips into dream. Tonight, you've tucked yourself into a corner of the universe just big enough for starlit questions and the soft hum of possibility. Now, I do hope this isn't too interesting that it keeps you awake, but if it does, well, at least you'll have learned something fascinating about the deepest nature of reality, specifically, what it might mean if our world is just a simulation. Before we begin, if you enjoy these slow science journeys, I'd be ever so grateful if you tapped the like button, subscribed, or even just left a comment telling me where in the world you're watching from and what time it is in your corner of the night. There's something comforting in knowing how connected we all are, sharing these moments of scientific wonder on our own sleepless nights. So, settle in, get comfortable, and let's begin our quiet voyage into the mind-bending possibility that everything you've ever known might be running on cosmic code. The curious question of, what if reality is just a simulation? To enter this topic gently, imagine the very notion that your life, your thoughts, and everything you experience could exist not as part of a fundamental physical reality, but instead as lines of code playing out with exquisite detail. Tonight we'll explore this idea with scientific scrutiny, but also with the soft curiosity that comes from lying quietly in the dark, pondering the impossible. The simulation hypothesis, as it's now often called, is both a mind-boggling scientific theory and a centuries-old philosophical puzzle. But don't worry, tonight we'll walk slowly through its mysteries, not to find concrete answers, but to understand what scientists, philosophers, and those endlessly curious among us have discovered so far. At first glance, the idea that we may live inside a simulation might sound like science fiction or video games gone wild. Yet, this question goes back much further than 21st century technology. For as long as people have gazed up at the stars and wondered why, there have been thinkers who questioned the very fabric of existence. Tonight, you'll learn how this dreamlike thought stitched itself into science, what experiments and evidence we have, and why you, drifting off to sleep, are living proof of the endless strangeness that reality offers. As we meander through hypotheses about computers powerful enough to hold universes, the quantum quirks that might betray our code, and the logic of those who say it's more likely than not we're simulated, my goal is not to unsettle, but to soothe, to help your curiosity find a peaceful place to rest. Whether you drift off or stay enchanted, let's gently loosen the knots of reality together and see what emerges when we ask, are we really here? Or are we lines of code in someone else's dream? Before silicon chips and virtual universes, before screens flickered with games so real your heart could momentarily forget the difference, the idea that reality might be a grand illusion flickered quietly in the minds of philosophers. To truly understand the simulation hypothesis, it helps to wander back through time, past glowing monitors and data centers, right into the candlelit chambers of ancient thinkers and dreamers. The question of whether the world is truly as it seems, or instead only appears so, has lingered like a gentle echo through centuries of reflection. Plato, one of the foundational figures of Western philosophy, left us the allegory of the cave around 375 BCE. Imagine, he said, people chained in a cave from birth, able to see only the shadows dancing across a wall, cast by objects behind them that they cannot see. Those shadows become their reality, the totality of what they know, but dramatically, it is all only a projection. Just outside their reach, the real world exists, entirely unseen. Plato's allegory was not about computers, of course, but about the limitations of perception and the seductive power of illusion. His cave now serves as a hauntingly prescient metaphor for simulated reality. If we've never glimpsed behind the code, how can we know what's real? Centuries later, René Descartes in 1641 pondered how one could know anything for certain. He proposed a now famous evil demon who could deceive all our senses, making us believe in a fabricated reality. This philosophical skepticism, questioning whether our senses are trustworthy, helped establish the groundwork for modern questions about simulation. Before graphics cards and physics engines, Descartes drew a line straight to the heart of doubt. If every experience could be cleverly forged, Could anything be believed as fundamentally real? Moving forward, we discover that early Hindu and Buddhist traditions also explored Maya, the illusionary nature of the world. Indeed, thinkers from across humanity's philosophical landscape have for thousands of years quietly suggested that what feels solid might in fact be a construction, a mirage, a play performed by something greater, be it deity or, as we contemplate today, a hyper-advanced intelligence. The idea lingered for centuries, contemplative and unprovable, until the 20th and 21st centuries brought about new metaphors. As digital technology blossomed, think of how, in just a few decades, we moved from the clunky mainframes of the 1940s to the immersive virtual realities of today. Suddenly, the metaphor of the programmed world became both literal and deeply plausible. The simulation hypothesis hasn't replaced the old philosophical doubts. It's simply reframed them with new material possibilities. This line of questioning, so gentle and yet so profound, has always been about reality's slipperiness, about how what you sense and what is true might not always be the same thing. Tonight, as you listen, you join a long lineage of curious minds, Plato's chained figures, Descartes' skeptical musings, and the meditative contemplation from ancient East to modern West. In this continuity, your quiet midnight wanderings are part of the same story. As we drift onward, remember, the simulation question is an old friend, always quietly nudging us to check if the world is really what it seems. Far from being simply a modern worry, it is perhaps one of the most ancient lullabies that the mind has ever sung to itself. So let's calmly wander from caves and shadows, past sleeping philosophers, into the rapid-fire world of digital thought, and see who next dares to answer whether we might live in a constructed world. After millennia of philosophical pondering, the simulation hypothesis was thrust into the scientific spotlight thanks to one especially influential thinker, Nick Bostrom. In 2003, this Swedish-born philosopher published a paper that became the foundation of modern simulation debate. A careful, logical argument, not just idle speculation, that challenged how we consider what is real. Bostrom's simulation argument is not merely a claim that the universe is probably simulated. Instead, it's a sober, mathematical proposal showing that under reasonable conditions, one of three outcomes must be true for any technologically advanced civilization, ours included. Let's gently unpack those now, as if smoothing the wrinkles from a sheet before sleep. The first possibility, Bostrom suggested, is that all civilizations at our level of technological development go extinct before they can develop the ability to create ancestor simulations, computer-generated realities so detailed and intricate that the inhabitants would themselves be conscious, sentient beings, as real as we are. In other words, intelligent life might always destroy itself, or be destroyed, before reaching this level of omnipotent computation. The second scenario, advanced civilizations do reach the point where running such simulations is possible, but, for some ethical, economic, or philosophical reason, simply choose not to. Perhaps the simulations are deemed dangerous or exploitative, and so, across the galaxy, nobody presses run. It's the third scenario, however, that truly unsettles the thoughtful knight. If technologically advanced civilizations survive and do create many high-fidelity simulations of their past, imagine millions or billions of detailed worlds, each lovingly crafted. Then, Bostrom argued, the overwhelming majority of beings with conscious experiences like ours aren't living in base reality. Instead, they exist in one of these simulations. If that's true, then statistically, it would be vastly more probable that you are simulated rather than one of the rare originals. It's important to note, Bostrom himself doesn't insist we are in a simulation. Rather, his argument is about probabilities and logic. His work was careful and technical, intended not to frighten or mystify, but to prod the thinking world into re-examining old assumptions with new scientific rigor. The simulation argument became a phenomenon in scientific philosophy, hotly debated from the dorm rooms of physics departments to the carefully modulated offices of computer theorists. Bostrom's paper led some notable public figures, like Elon Musk, to publicly muse that our chances of living in base reality may be 1 in billions. Yet, for those inclined toward cautious skepticism, It's a prompt for deep curiosity rather than simple acceptance. Many scientists and philosophers continue to discuss the challenge of testing this argument, its assumptions, and the nature of consciousness itself. His work also reignited a fundamental question. Even before digital computers, was reality always, in some sense, computable? Are the workings of the cosmos simple enough to be entirely described as information patterns, algorithmic, ready for simulation, or are there mysteries forever beyond code and calculation? Bostrom's approach encourages active examination, testing assumptions, analyzing probabilities, and distinguishing between what we hope and what we can actually prove. The impact of this hypothesis has extended far beyond philosophy seminars. It echoes through physics, cognitive science, and even popular culture. Movies, television, novels, and art have embraced the possibility of simulated worlds as a lens through which to examine meaning, responsibility, and possibility itself. It's proof, perhaps, that even the wildest questions can become part of our most important scientific explorations. As you settle more deeply into relaxation, consider, in every age, humans have questioned what cannot be directly seen. Bostrom's argument is just the newest shade of an ancient wonder, rooted not only in dreams, but in the rigorous logic and mathematics that underlie modern science. The question remains open, and there are many passionate voices on all sides. Sleep comes a little easier, perhaps, when we know that, whatever the answer, it has become a mystery both grand and worthy of our careful, gentle consideration. As we nestle further into the mystery of simulated reality, it's time to consider a force that has quietly transformed our world, weaving the fantastical into the fabric of the ordinary, computing power, and the astonishing progression known as Moore's Law. If you've ever wondered how realistic video games or breathtaking special effects are possible, or how a single device fits the world in your hand, you've brushed up against this constant acceleration, a kind of digital heartbeat that could one day make simulations of entire universes thinkable. The principle called Moore's Law was coined by Gordon Moore, the co-founder of Intel, back in 1965. He observed that the number of transistors on a microchip, the tiny switch-like devices that handle all the thinking in computers, tended to double every 18 to 24 months. Put simply, this meant that computers were becoming exponentially more powerful over time, while costs shrank and devices became smaller and more accessible. The implications were profound. In a world where your phone is more powerful than the computers that sent humans to the moon in 1969, it doesn't feel so outrageous to whisper about worlds within worlds. Think about this for a moment. The original Apollo guidance computer had about 64 kilobytes of memory and operated at just 0.043 megahertz. Today's smartphones, by comparison, can have millions of times greater processing ability. For decades, this leap continued almost like clockwork, creating a cascade effect, enabling everything from detailed graphics for games and scientific simulations to the beginnings of artificial intelligence. In the context of the simulation hypothesis, Moore's Law is more than just a curiosity. It's a foundational pillar of plausibility. If the pace of computational growth continued for long enough, with what's known as exponential progress, eventually, it's conceivable that a sufficiently advanced civilization could command enough resources and processing to replicate sensory inputs, thoughts, memories, and entire living histories indistinguishable from the real thing. You can imagine each atom, each physical law rendered by instructions in the ultimate computer, but there is nuance worth noting. Lately, the predictability of Moore's Law has begun to waver. Physical limits of silicon, heat dissipation challenges, and the strange antics of quantum mechanics at atomic scales indicate that the endless doubling can't persist forever, not in the same form at least. Engineers are now exploring new paradigms, quantum computers, DNA-based processors, neuromorphic chips that mimic the human brain, even speculative concepts like their universal quantum simulators. Why does this ongoing technological evolution matter so much to the simulation debate? Because the feasibility of any simulated universe depends on computation. How much can be processed? How efficiently? And at what cost? If rooted only in silicon chips, a universe-sized sim might be impossible or take eons to complete. But if computation is a law of nature, endlessly scalable through innovation, then the odds tilt. It's not just about raw power either. Advances in software, algorithms that compress, predict, and fake complexity, allow ever more convincing digital environments to be rendered with less effort. Consider, for example, how clever code lets a simple video game depict a vast city without modeling every individual citizen in detail. Instead, important details are filled in only when needed, a trick borrowed from nature itself, where your eyes and brain ignore most of what's around you, focusing resources on only what's relevant at a given moment. All these advances, faster processors, better memory, smarter code, suggest that if a sufficiently patient and ingenious civilization existed, and if they wanted to, the technical barriers to simulating mind and matter, sensation and memory, might eventually fall. So the next time you unlock your phone or marvel at a new game's lifelike realism, remember, you're seeing the faintest shimmer of what Moore's law could ultimately enable, echoing the possibility that somewhere, an unseen programmer might one day have the means to weave an entire reality around conscious minds just like ours. As you close your eyes and your thoughts drift to quieter places, know that the silent hum of every computer, everywhere, is the chorus of billions of tiny switches, moving technology a heartbeat closer to the realm where the simulated and the real become indistinguishable, at least for sleepy scientists and dreamers alike. Now that we've gently traced the arc of computational progress, it's time to define clearly what scientists actually mean by a simulation. In scientific and computer science terms, a simulation is a systematic imitation, an engineered recreation of the behavior, rules, and processes of a real or hypothetical system, brought to life within a mathematical or digital framework. Whether it's a weather forecast, a working model of the solar system, or a virtual ecosystem swarming with programmed creatures, a simulation is an echo, not the reality itself, but a careful and often predictive reflection of it. To ground this idea, consider the roots of modern scientific simulation. In the mid-20th century, physicists, chemists, and engineers began harnessing early computers to model processes that were too unstable, large-scale, or dangerous to test in real life. One of the most famous early examples is the Monte Carlo method, named by nuclear physicist Stanislaw Ulam and mathematician John von Neumann, first deployed in their calculations at Los Alamos in the 1940s. This method uses countless random samples to predict outcomes of uncertain events, for example, simulating how radioactive particles might spread, or how molecules interact in a new chemical reaction. Even today, Monte Carlo simulations remain foundational in everything from climate models to Wall Street algorithms, showing how deep and versatile the concept really is. At its core, a simulation replicates the rules and logic of a system to produce an experience, set of data, or stream of results that closely mirrors what would happen for real. In digital simulations, this replication unfolds using code. Think of lines of software instructions, millions, sometimes billions, specifying how every part of the system interacts, how every force or choice is handled. On modern computers, these rules can describe not only numbers, but visuals, sounds, and even the subjective experiences of intelligent agents, at least in a basic form. It's this conceptual leap, from simulating weather to simulating minds and entire universes, that makes the idea of a simulated reality not just a flight of fancy, but a tangible question of engineering. In recent decades, the ambition and complexity of simulations have grown exponentially. In astrophysics, scientists now create vast virtual universes, entire cosmologies filled with millions of simulated galaxies, stars, and planets, all swirling with gravitational and quantum rules. These projects, like the illustrious Millennium simulation completed in 2005, use powerful supercomputers to crunch unimaginable quantities of math, weaving digital realities so intricate that they've actually led to real-world discoveries about how the cosmos unfolds. And in neuroscience, researchers attempt to simulate the entire human brain, neuron by neuron, to unlock how thoughts, memories, and personalities emerge from microscopic electrical pulses and chemical reactions. Why does this matter to you, trying to fall asleep under your familiar ceiling? Because these simulations are limited only by technology. They are not fundamentally different from the world you experience, at least in structure and logic. In principle, if you can simulate the behavior of a thunderstorm, a galaxy, or a handful of cells, there's no reason, beyond computation limits and philosophical unknowns, that you couldn't simulate the totality of conscious experience, the silent play of thoughts and emotions behind your eyes. Computer scientists often debate the difference between a simulation and reality. One working definition is that a simulation is any environment in which rules are applied and outcomes observed, separated from the base reality by a layer of mediation, what we might call code or calculation. In that sense, if the universe is described by unwavering mathematical laws, some seasoned thinkers argue, it may behave very much like a natural simulation, with no computer required. But the simulation hypothesis invites an even more provocative picture that conscious experience is seated not in a physical universe at all, but in a virtual world, a sophisticated program possibly running on some advanced substrate far beyond our detection, blurring the already fuzzy line between what is simulated and what is fundamentally real. In practical terms, you encounter simulations every day in ways both subtle and powerful. Weather forecasts, traffic models, economic projections, and even the smart predictions your phone makes are all built on millions of running simulations, trained to replicate, predict, and sometimes even improve upon reality. The science of simulation is a living testament to humanity's drive to understand, to imagine, and ultimately, to recreate. And every step forward, from Ulam's nuclear calculations to present-day brain mapping and galactic modeling, brings the age-old question into sharper focus. If we can simulate the world in ever greater fidelity, how can we be sure that our own world isn't itself a simulation created by someone, somewhere curious enough to imagine us? As you drift further, consider this. The boundary between real and simulated may not be as impenetrable as intuition suggests. Each simulation mimics the laws of its parent reality, but the logic that binds these worlds together, mathematics, physics, chemistry, remains eerily consistent, layer upon layer. You, the listener, are both observer and participant in a dance of informational patterns, quietly pondering. Might this too be a simulation, born of rules, running softly just for you? Let's gently draw closer to the frontier where computer science meets physics, a borderland that has recently blossomed with the idea that our universe itself may not be continuous and infinitely divisible, but rather pixelated at some unimaginably tiny scale. This perspective, sometimes called digital physics, wonders if the deepest fabric of the cosmos is not smooth, but quantized, divided, like a vast cosmic screen, into a grid of indivisible units. The notion brings an oddly comforting symmetry to the simulation debate, bridging the gap between the familiar world of digital technology and the exotic rules of nature. To begin, think about how digital images are constructed. If you zoom in tightly on any photograph on your computer, the seamless scene eventually dissolves into a mosaic of colored squares, pixels, each one distinct and separate from the others. In computer graphics, these pixels are the smallest building blocks of an image, and the illusion of smoothness arises only when viewed from a distance, when your brain knits them together into a single coherent whole. So too, say some physicists, might the fundamental structure of space and time be composed of discrete elements, not pixels in the visual sense, but quanta of space, a kind of subatomic latticework, so fine and subtle that even our most powerful tools can't resolve it directly. At the heart of this speculation lies a branch of theoretical physics called loop quantum gravity, proposed in the 1980s by physicists like Carlo Rovelli and Lee Smolin. Loop quantum gravity suggests that space itself is quantized, composed of exceedingly tiny, Planck-scale loops that combine to create the world as we experience it. But even before quantum gravity, hints of nature's digital structure had already appeared. Quantum mechanics, the revolutionary science of the unimaginably small, insists that energy, matter, even light itself, all arrive in discrete, indivisible packets, quanta. Electrons leap between levels, photons shower from excited atoms, all in sudden, stepwise motions instead of smooth classical flows. These discoveries led some bold thinkers, like John Archibald Wheeler, to propose in the mid-20th century the provocative motto, "It from bit." Wheeler wondered aloud if information, rather than matter or energy, was the true foundation of existence. The universe, in his view, might not just behave like a vast computation. It might literally be one, with physical laws as lines of code and the stuff of reality itself as bits in an unfathomable cosmic register. Critics note that while digital analogy is intriguing, we lack direct proof that the universe is pixelated. But interestingly, many cutting-edge physical theories are at least compatible with this idea. In modern cosmology, researchers search for signs that the smooth continuum of space and time might break down at the Planck scale, nearly 10 to the minus 35 meters. That is so small that, to a human mind, it might as well be zero, but in principle, it sets an ultimate resolution on the cosmic display. What would it mean if there was actually a finest possible grain to reality? For one thing, it would place strict limits on how finely any simulated universe, ours or otherwise, would need to be modeled. No need for infinite complexity. A grand simulation could simply update each pixel as needed, just as your screen only refreshes the part you're looking at. In effect, this digital physics worldview says, if we ever find the universe operates like a vast grid or lattice, with information as its true currency, that would be precisely the trick a simulation would employ to conserve resources. But the most beautiful aspect of this digital perspective is its unity with technology. The same fundamental principle that allows engineers to precisely reproduce worlds on a computer, the discretization of data, the trust in quantized bits, might lurk beneath the cosmos itself. Some have gone so far as to speculate that if we one day detect a kind of resolution limit in nature, a point at which smoothness breaks down completely, it could provide indirect evidence that we're inside a simulated environment governed by finite programmable units. As the hour grows late and your mind floats in soft uncertainty, remember this: the tiniest, most elusive scaffold of reality might not only hold up galaxies, but reflect the familiar logic of every digital world you've ever known. If the cosmos is structured in discrete steps, not endless smoothness, it won't just unite science and mathematics. It will quite literally bring the question of simulation home, pixel by pixel, into the core of every star and every silent, dreaming thought. If you're still with me, cozy and curious, let's explore a wonderfully peculiar corner of science, where the deeply counterintuitive phenomena of quantum physics have stirred the imaginations of many who ponder simulation theory. For in the realm of the very small, where particles flit in and out of existence, reality seems to act more like carefully written code responding to user input than the continuous, predictable machine early scientists once imagined. How can this be so? Let's gently drift through these quantum mysteries together, unraveling just how their code-like nature has nudged so many thinkers toward the simulation hypothesis. Begin with one of the most famous experiments in science, the double-slit experiment. When a single electron or photon is fired at a screen with two slits, something astonishing happens. If no one is measuring which slit it goes through, the particle behaves like a wave. It seems to travel through both openings at once, interfering with itself, and creates a pattern of dark and light bands on the far wall. But if you try to observe which slit the particle actually passes through, the interference pattern disappears, as if the universe collapses the wave and makes the particle choose a definite path. The act of observation somehow changes the outcome. Does this not sound like a feature written into a program? In a computer game, the system only renders what the player can observe, saving computational resources by creating details on demand. Some physicists and philosophers, most famously in the field of quantum information theory, have marveled at how the mechanics of quantum measurement resemble conditional code. If observed, do X. If not, continue with Y. The simulation hypothesis draws strength from this parallel, suggesting that perhaps the universe runs only the details you can perceive, less like a static, independent reality and more like interactive software. Take 2, the phenomenon of quantum entanglement, described by Einstein as spooky action at a distance. When two particles become entangled, their properties are mysteriously linked, no matter how far apart they travel in space. Measure 1, and the state of its twin is instantly determined, faster than any signal could possibly travel. Some simulation theorists have wondered if this instant linkage resembles a kind of shortcut in the underlying code, where a rule is enforced not by information traveling across space, but by a single update to a shared variable hidden deep in the machinery of the simulated world. Quantum weirdness goes even further. The principle of superposition allows particles to exist in multiple states simultaneously, but the moment you interact with them, ask them a question, so to speak, they seem to decide on an outcome. As sleep creeps in, consider how this mirrors the way random events are resolved in a complex simulation. Probabilities collapse only when the result matters, not before. But perhaps the grandest code-like rule is found in nature's math itself. The physical laws governing our universe, expressed in compact, elegant equations, are astoundingly repeatable and precise. The fine structure constant, for example, is roughly 1/137th, dictating the strength of electromagnetism, and it remains constant everywhere that we have been able to look. Gravity unfailingly pulls with the same force at every point in space. The masses of subatomic particles, the charge of the electron, the speed of light, these numbers sit like lines of code, immutable variables set at production. The uncanny precision, some have argued, is suggestive of carefully chosen settings in a gigantic simulation, tuned just so to allow for complexity, chemistry, and consciousness. Of course, it's also worth acknowledging that most physicists do not take these features as proof we are simulated. Quantum mechanics, for all its strangeness, stands on a solid experimental foundation. The rules are what they are, and so far, they match reality to breathtaking precision. Still, these law-like regularities and the strange observer-dependent nature of quantum events mean that simulation theory can never be fully ruled out on empirical grounds alone, at least for now. What's most soothing about recognizing these code-like laws is how intimate they are, touching even the farthest corners of your own existence. The energy surging through your nerves, the light cascading onto your eyes right now, all dance to the tune of quantum rules. And whether or not they were programmed by an external designer, there's joy in knowing that the universe, on its smallest scales, is far stranger than dreams, and possibly, just possibly, designed to be discovered, question by question, in these hushed nighttime wanderings. As your thoughts begin to float, remember, the universe's programming, whether real or imagined, has written you a lullaby of questions, a quantum story, rendered soft and strange, just for the seeker tucked in and listening tonight. As we drift further into the gentle twilight between science and speculation, it's time to turn the gaze inward, into the mysterious machinery that makes sense of the world, your own senses and the brain that interprets them. The notion that reality could be a simulation depends not just on physical or computational possibility, but also on the profound truth that what we call reality is constructed entirely from signals received, processed, and synthesized by our own biological systems. In truth, you do not experience the world directly. You experience your brain's exquisitely detailed interpretative rendering of the data that streams in through your body. Let's explore that softly. Right now, as you listen, your ears translate air vibrations, pressure changes stirring the delicate hairs in your inner ear, into streams of nerve signals that speed into your auditory cortex. Your brain then assembles meaning, the tone of my voice, the rhythm of words, perhaps even the imagined space around them. When you open your eyes, photons, mere packets of light, strike the cells of your retinas, sparking electrochemical reactions. Out of this storm of information, your brain constructs a colorful three-dimensional world full of texture and depth. But this orchestration is, at its core, a simulation within your skull. The brain seamlessly blends raw inputs with memory, expectation, emotion, and learned patterns. Researchers have demonstrated countless ways that the mind not only interprets, but fundamentally shapes what you perceive. Optical illusions, like the spinning dancer, or the impossible trident highlight that your senses can be easily tricked, often seeing motion or dimensions that don't exist on the page. Even more subtly, phenomena like change blindness prove that you can miss enormous shifts in your visual environment, even if you are looking right at them, because your mind prefers to fill in the gaps with what it predicts should be there. Consider also the way the brain filters the overwhelming data that bombards it every moment. The human retina might send over 1 million signals per second, while your conscious mind only handles a tiny select stream. Most sensory input is automatically discarded, compressed, or categorized, much like a clever computer program only loading what's needed to render a scene in a video game. The world out there is far too complex for your conscious awareness to process in perfect fidelity. As a result, your perception of reality is more like a best-guess rendering, a beautifully adapted simulation, optimized for survival rather than pure accuracy. If you think too about the boundaries of your perception, of light, of sound, of heat, you realize there are many realities just beyond your reach. Human eyes see only a narrow band of the electromagnetic spectrum. Ultraviolet rays bathe the world in hidden patterns insects can see, while infrared warmth glows for reptiles but not for us. Bats and dolphins navigate with ultrasonic sound, mapping a world that is silent to you. Our ears, skin, and noses, too, provide only partial maps of what's really there. Neuroscience gently confirms that our brains are prediction factories, sculpting experience from snippets of evidence. The late neuroscientist Carl Friston developed predictive coding theory, which proposes that the brain is constantly constructing a running internal model of the world, checking incoming signals against expectations and updating accordingly. This quiet, relentless simulation is what keeps the world stable and familiar, and is why, even when you're dreaming, the textures, spaces, and emotions of your mind can feel vividly real. As these layers of interpretation accumulate, it becomes both scientifically and philosophically reasonable to entertain the thought. If your brain is already simulating a version of the world based only on sampled and filtered data, then a more fundamental simulation, run by some external entity, could, in principle, provide all the information needed for you to experience life as you do. You are never in unmediated contact with the world itself, but with your cortex's best rendering in real time. So, as you lie quietly, eyes perhaps growing heavy, consider this. The interface between self and world is always a creative performance, tailored to your needs, history, and biology. Whether or not you're in a grand computer simulation, you are certainly participating in a simulation every moment. The endlessly adaptive, imperfect, and yet wondrous model your brain produces as you go about your night, and by slip into dreams. Let's now turn to the quietly unnerving question posed by statistics. If advanced civilizations could create vast numbers of simulated realities, what are the chances that you, right now, are existing in one of those artificial worlds rather than in the base or original reality? The answer, as posed by several modern philosophers and mathematicians, is both astonishing and deeply thought-provoking. It suggests that, in a universe where high-fidelity simulations are common, the odds might be stacked heavily in favor of most conscious beings, and thus, perhaps, you being simulated. To gently unpack this idea, imagine first a scenario with just one ancestral civilization that survives technological infancy and gains the power to conduct ancestor simulations, detailed recreations of their evolutionary or technological past, designed for research, curiosity, or even entertainment. If such a civilization were to create just a handful of these simulated worlds, each containing billions of conscious minds, the number of simulated beings would quickly surpass the number of real beings in the original history. If each simulation spawns further simulations, as software can be infinitely copied and forked, the numbers balloon still further. This is the logic that underpins Nick Bostrom's famous probability argument, but it also arises in fields like statistical cosmology and computer science. If we accept two major premises, one, that it's physically possible to simulate a universe like ours with beings who are conscious, and two, that at least one civilization somewhere actually does this, then it becomes a mathematical question. The overwhelming majority of conscious experiences, by sheer number, would arise within simulations, not in the base reality. How dramatic is this imbalance? Picture that there is one base civilization and, conservatively, 1,000 simulations are created over millennia. Each simulation contains as many conscious entities as the real world does. Billions, perhaps even trillions, if time or history is accelerated for the sake of gathering data. Under these assumptions, for every original, there are at least thousands, maybe millions, of simulated counterparts. If you were to randomly wake up in a mind somewhere in this system, the odds of being a simulated mind vastly outweigh those of being an original. Some thinkers, like the astrophysicist Paul Davies, have explored this mind-bending possibility in the context of cosmological models and information theory, highlighting the way that large-scale probabilities can fundamentally change our perspective on existence itself. It's a gentle but unnerving statistical sleight of hand. You do not observe the outside world directly, so you cannot determine from the inside whether your world is singular or whether it's one of many stacked inside computers whirring somewhere far beyond your awareness. Of course, this argument rests on several key assumptions, each debated in scientific and philosophical circles. First, it's not currently settled whether simulating consciousness is ever truly possible. Perhaps there are unknown laws of physics, or consciousness is bound to some irreducible property of biology that cannot be technologically recreated. Second, advanced civilizations might find ethical or practical reasons to avoid creating enormous numbers of simulated minds. And finally, we do not know whether the energy and computational resources available to any civilization, no matter how advanced, can actually meet the theoretical demands of simulating complex, conscious-filled universes. Nevertheless, as a matter of probability, if simulations can and do occur, and if they are created in vast numbers, you are vastly more likely to be living in one than in the elusive base reality. This inference, resting directly on the mathematics of large numbers, is both comforting and disorienting. Comforting perhaps because it means your experiences, feelings, and consciousness are just as real as they seem, regardless of their origin. Disorienting because it undermines the assumption that the reality around you is the fundamental one, rather than a mindfully designed echo. The statistical argument for simulation is not airtight proof, but rather a powerful nudge, a logical invitation to consider the immense scale of what might be possible if even just one civilization somewhere learns to dream in code. So as you rest, ponder this. The sheer mathematics of simulated worlds, like the stars above you, are vast, humbling, and as yet unproven, leaving your curiosity suspended between awe, number, and wonder, ready to slip quietly into restful dreams. The universe, as experienced from within, rarely reveals its workings in the form of visible seams or cognitive glitches. Yet, if our reality is a simulation, you might wonder if, just sometimes, there could be telltale signs, a skipped frame, an unexpected quirk, a logic error echoing the way a paused video game or a malfunctioning app momentarily betrays the code pulsing beneath the surface. Tonight, let's drift with gentle curiosity through the scientific and philosophical quests to find such glitches in the matrix, the evidence, however subtle, that our world might be more artificial than it appears. One of the more famous approaches stems from the idea that if the universe is simulated, its code might occasionally falter or reveal artifacts of digital construction. Researchers like physicist Silas Bean at the University of Washington have even proposed concrete tests. In 2012, Bean and colleagues suggested that if our universe were being simulated on a discrete space-time lattice akin to pixels on a screen, then high-energy cosmic rays, as they travel through space, would display a detectable, grid-like limitation in their paths, just as the movement of characters in a video game is limited by the screen's resolution. So far, no such telltale pattern has been observed, but experiments are ongoing, pushing the limits of our measurements to ever finer detail. Another avenue for potential evidence is found in the peculiar consistency of physical constants, those unchanging numbers like the speed of light, the mass of an electron, or the gravitational constant that seem to be hardwired into the universe. While their unyielding precision might simply reflect the deep order of nature, some have wondered if these constants act as settings, fixed in a program, perhaps for ultimate stability or elegance. Until we see these values randomly alter or discover more configurable universes, it's speculation, but an intriguing one. Sometimes people point to everyday oddities, those strange moments when the world seems to act inexplicably, almost as if a bug has slipped through quality control. Déjà vu, the uncanny feeling that you've experienced a present moment before, is one such example often cited in popular culture. While neuroscientists explain déjà vu as a misfiring between short-term and long-term memory circuits, believers in simulation theory like to muse that this could be a momentary reset or data overlap in the simulation's memory. Rest assured, science leans on the brain's quirks, but it's a fun, if unproven, metaphor for a world with hidden code. Another glitch chaser perspective comes from quantum physics. As discussed earlier, the observer effect and quantum randomness feel unnervingly like the lazy evaluation in computer programming. The universe, it sometimes seems, only resolves what you test, and not before. Some have searched for evidence of this in unexplained correlations or deviations in noisy quantum experiments. But so far, robust proof is lacking. On the more philosophical side, the simulation hypothesis is haunted by the possibility that any sufficiently advanced designer could easily create a simulation without detectable flaws. When you craft a digital landscape in a video game, you can patch out bugs, create redundancy, and hide the machine's workings from the player entirely. If our world were built by truly advanced beings, let's call them post-humans for now, then perhaps their skill ensures that glitches never appear. Or if they do, they are resolved before affecting the conscious experience of simulated agents. There is also the sobering possibility that searching for glitches may be an unreachable goal, a bit like a character in a novel trying to read the text of their own story. Some theoretical physicists, such as Max Tegmark, argue that unless a bug in the code manifests as a statistically clear deviation from the laws of physics as we know them, we would not be able to distinguish a simulation from a perfectly running natural universe. Any evidence might be forever out of scientific reach. Yet, the effort continues. Particle physicists and cosmologists constantly scrutinize astronomical and subatomic data, sifting for deviations that could signal something deeper, be it new physics, a change in cosmic structure, or even an artifact of simulation. So far, everything matches the painstakingly precise equations of established science. But this ongoing search, the curiosity to peek behind the curtain, remains, in its own way, a testament to the scientific spirit. For now, no confirmed glitches or mistakes have punctured the seamless veneer of reality. If you ever notice a strange moment, a fleeting pattern in the stars, a paradox in a dream, enjoy it as evidence of your mind's unrelenting creativity and the universe's endless subtlety. The mystery remains intact, both science and lullaby, inviting you to drift ever deeper into a world where possibilities exceed the boundaries of certainty, and every oddness is an invitation for deeper wonder. To explore another gentle avenue in our quiet quest, let us consider a foundational notion drawn from the heart of physics, mathematics, and computer science, that information, not matter or energy, could be the true bedrock of the universe. This perspective, embraced by some of the most creative minds in modern science, suggests that the cosmos, at its most irreducible core, is fundamentally mathematical, defined by the storage, transmission, and transformation of pure information. In this framework, our everyday sense of solid objects and flowing energy becomes a wondrous illusion, built atop vast, intricate webs of informational code. Begin by pausing on the work of Claude Shannon, the father of information theory. In the 1940s, while working at Bell Labs, Shannon showed that every form of communication, sound, text, images, even genetic code, could be distilled to information, series of yes or no choices, or in digital terms, bits. His insights laid the groundwork for every digital technology in use today, transforming telecommunication, computer science, and eventually how physicists describe reality. Shannon's bit, standing for binary digit, is the smallest possible unit of information, much as an atom is the smallest chemically indivisible unit of matter. But what does it mean to say the universe is built from information? Take John Archibald Wheeler's influential phrase, "it from bit," the notion that every physical thing, every it, ultimately arises from simple yes or no informational events. Wheeler suggested that the root level of reality is not substance, but data, binary alternatives, quantized choices. Whenever a particle's position is measured, a bit is created. Every quantum event, then, is the whisper of an answer to a cosmic question, accumulating stitch by stitch into the world you see. This isn't merely poetic. In black hole physics, Stephen Hawking's and Jacob Bekenstein's work in the 1970s showed that the information content of a black hole, everything about the particles it consumes, is not lost, but encoded on its event horizon in discrete bits. This led to the bold holographic principle proposed by Gerard Hooft and Leonard Susskind, which posits that all the details of a three-dimensional universe may actually be stored on a two-dimensional surface, like a vast cosmic hard drive, encoding the deep story of space and time in informational pixels. The more researchers probed, the more they found that the laws of nature operated not unlike algorithms, evolving state by state, as though ticking through a set of computational instructions. Quantum physics, too, has joined this informational chorus. Theoretical physicists like Vlatko Vedral argue that reality is not what it seems, because it is fundamentally about relational information, about how quantum bits, qubits, link together to define the state of the universe. Everything you see, trees, clouds, cats, and even the thoughts drifting across your night, may arise from exquisitely complex patterns of information, interacting and collapsing in space-time. How does this tie into simulation theory? If the universe is best described as information processed according to rules, it strongly resembles the architecture of computation. Every simulated world, from the simplest video game to a grand ancestor simulation, is fundamentally a theatre of bits brought to life through programmed rules. Recasting the universe as mathematical information blurs the line between nature and simulation, suggesting that what we experience as reality could, in principle, be implemented in many substrates, from silicon chips to unknown higher dimensional mechanisms. As experimental evidence, consider how cutting-edge physics experiments now treat information as a physical quantity. The Landauer limit, named after IBM physicist Rolf Landauer, defines the minimum possible energy needed to erase one bit of information, showing that computation, heat, and matter are inextricably linked. Meanwhile, scientists use quantum information theory to unlock puzzles about teleportation, encryption, and even the fate of information at the boundaries of black holes. In your daily life, the information-centric universe is quietly present. Your thoughts, your memories, the very structure of your DNA, all are encoded, stored, and transmitted as information. The neurons in your brain fire according to encoded patterns, and your body operates seamlessly, as if running the most advanced biological software. So gently, as you drift softer into rest, remember, whether our universe is simulated or not, it is at least deeply informational, a tapestry of code and logic woven into every atom and every star. And if some cosmic programmer once decided to run a universe like ours, they too would be bound by these immutable truths, that to create, to simulate, to live, is to process and cherish information in all its infinite, awe-inspiring abundance. Let's relax even further by returning from the distant cosmos to something more immediately familiar, the rapidly evolving world of virtual reality and computer simulations right here on Earth. If you've ever slipped on a VR headset, become lost in a lifelike video game, or simply marveled at how digital characters can feel eerily real, you've glimpsed firsthand how technology is rapidly blurring the boundary between the fabricated and the felt. These creations are not only entertainment, they serve as small laboratory worlds, letting us explore what it might mean to simulate, modify, or even produce meaningful experiences within an artificial environment. Virtual reality, as a scientific tool, is more than just a technological curiosity. Scientists use VR environments to study behavior, cognition, and even social interactions. For example, researchers at Stanford University's Virtual Human Interaction Lab have constructed detailed digital spaces where volunteers interact with avatars. These studies explore empathy, prejudice, and the flexibility of human psychology. Participants often finish an experiment feeling as if their experiences, flying, facing a virtual crowd, navigating impossible environments, carried emotional resonance and personal memory, blurring the line between lived reality and artificial construct. Beyond psychology, VR and computer simulations have profoundly transformed scientific research itself. In medicine, surgeons employ hyper-realistic simulations to practice delicate procedures. Every slice, suture, and touch is modeled in precise real time, down to the millimeter, helping train new doctors in risk-free environments. In aerospace, flight simulators let pilots fly every variety of aircraft through every conceivable weather condition, not just for training, but to explore rare emergencies too dangerous to repeat in the air. Of course, as technology marches on, the gap between simulated and real shrinks further. Games like No Man's Sky or The Sims generate vast, complex environments with millions of interacting agents, each programmed with behaviors that, at scale, feel spontaneous, even unique. In early 2023, researchers at the Massachusetts Institute of Technology used powerful artificial intelligence to simulate virtual societies composed of digital agents capable of conversation, memory, even evolving personalities. These agents built social connections, started clubs, planned parties, and gossiped about each other. For a human observer, the border between programmed response and lifelike behavior came thrillingly close to indistinguishable. This swift progress isn't only for entertainment or research. It offers living proof that richly immersive, interactive worlds can be created with complex rules, causal relationships, and increasingly, emotional resonance, each step providing a powerful analog to the potential structure of a simulated reality at cosmic scale. Philosophically, experiments in VR nudge us to ask, how real does an experience need to feel before we treat it as meaningful? In 2020, neuroscientists demonstrated that memories formed inside virtual environments, even those that were physically impossible, like walking upside down, were processed by the human brain with much the same emotional and mnemonic weight as real events. Your brain, in short, codes reality not by the material source of an experience, but by its internal consistency, sensory vividness, and emotional salience. This realization extends into artificial life, computer programs that simulate the behaviors of living systems, from simple digital ants who forage for food to complex ecosystems evolving over thousands of simulated generations. These models have become central to research in ecology, evolutionary biology, and even economics. Years ago, research by Chris Langton and others showed that digital organisms could evolve, reproduce, and compete, all governed solely by bits and rules. In a real sense, life, consciousness, creativity, adaptation emerges whenever the complexity and feedback loops are sufficiently rich. As you lay there, drifting further, realize, every day, scientists, engineers, and artists prove that it is possible for experiences to emerge from code, for environments to shape memories, and for rules to yield worlds. The boundary between waking and dreaming, real and simulated, physical and virtual, becomes ever more blurred with each technological leap. If, one day, the power of simulation is strong enough to render entire histories indistinguishable from our own reality, it will be the careful steps made in today's digital laboratories, the patient work of craftspeople and scientists alike, that have laid the path. Let these gentle truths comfort you. Your mind is already equipped to explore and adapt to any reality, even those built from bits and code. Every virtual step, every digital sky, every shared moment with an artificial other is simply another piece in the great puzzle of what it means to know, to feel, and perhaps, quietly, to be simulated. With our journey now rich in technical details and historical reflection, let's gently cross over into the soft terrain of philosophy, where the implications of living in a simulation stretch deeper than code and circuitry, touching the very core of consciousness, free will, and the meaning we ascribe to our lives. If in some far future or hidden present, a simulated universe contains beings who laugh, dream, and question their existence, how does that change what it means to be real? What does it mean for your sense of self, your choices, and your love for the world? Let's begin with consciousness, that mysterious quality that lets you experience the world, savor a memory, or marvel at the stars. If a simulation can perfectly imitate the neural complexity of a human brain, producing the same intricate dance of electrical signals, neurotransmitters, and learned associations, many philosophers and neuroscientists argue there is no obvious reason why consciousness should not emerge. From this viewpoint, simulated minds would not just behave as if they are sentient, but would truly feel, taste coffee, ache from loss, or wonder in the quiet of the night, exactly as minds in a base reality do. This proposition, sometimes called substrate independence, is rooted in extensive scientific thinking about how consciousness arises. If it is patterns, not substance, that matter, complex information flows, regardless of what medium hosts them, then consciousness could theoretically bloom wherever those patterns are recreated. This holds whether they are made from neurons and glia, or from circuits and code. But the ethical dimension soon arrives. If it is possible for simulations to host conscious lives, responsibility follows. What duties, if any, do simulation creators owe their simulated beings? Philosophers like David Chalmers have urged that simulated entities must be regarded as having rights, freedom from unnecessary suffering, perhaps even a chance to shape their own destinies. In your own life, this raises an unexpected form of kinship. Your thoughts and feelings, were they simulated, would be no less meaningful than anything in a physical world. The quality of experience, not its substrate, becomes most important. Freely acting within a simulation also invites the riddle of free will. Are your choices truly your own, if your world is governed by algorithms, or could you be nudged by hidden variables chosen by a programmer? Interestingly, these questions echo classic debates in natural philosophy and neuroscience, whether all our actions are determined by the immutable laws of physics, or if genuine freedom arises from the unpredictable quantum background noise in our brains. In a simulation, choice remains just as meaningful, for you act upon the information available, perceive, deliberate, and decide, shaped by memory, desire, and chance. Whether source code or neurons, this gentle mystery remains unsolved, and perhaps uniquely yours to interpret. Now consider meaning itself. Would your life's triumphs and tribulations matter less in a simulated reality? This is a question posed by thinkers from René Descartes to Nick Bostrom, each echoing the sentiment that the experience of meaning comes from participation, the love you give, the curiosity you nurture, the comfort you share. No matter the world's underlying substance, if joy, sorrow, and wonder are real to you, then meaning emerges, by your hand, in your heart. This inquiry becomes especially beautiful as it soothes the anxiety of uncertainty. Suppose, just for a moment, that our universe is a simulation. Even so, the pursuit of knowledge is not meaningless. Far from it. Grasping scientific laws, uncovering patterns, developing solidarity with others simply enriches the experience offered by the simulation. You contribute, you explore, you create, and your impact ripples outward, within whatever boundaries the system allows. As dusk gently folds over your thoughts, remember that these philosophical questions are not just intellectual puzzles, but invitations to self-reflection. Whether reality's code is quantum or computational, your capacity to reflect, to care, to shape meaning remains the truest beacon of what it means to be alive. And perhaps, most profoundly, what it means to be conscious anywhere, in any universe. Now, as your thoughts grow slower and the world hushes around you, let's wonder about the immense scale required to simulate an entire universe, perhaps even the computational power needed to mimic every detail, from the dance of galaxies to the gentle rise and fall of your own breath. The idea of simulating reality is thrilling, precisely because it forces us to reckon with both the immensity of the cosmos and the audacious ingenuity that such a feat would demand from its creators. To begin, let's start small and then spiral outward. In a basic computer simulation, whether it's modeling the weather or running a video game, every object, particle, or decision is calculated by underlying code. The more detailed the simulation, the greater the necessary computing resources. Now, imagine extending this approach to an entire universe, simulating every star, every leaf, every single atom across billions of light years, and for our purposes, simulating conscious experiences down to exquisite detail. Let's bring in some numbers. Researchers have estimated that in our observable universe, there are roughly 10 circumflex 80 atoms, a 1 followed by 80 zeros. To simulate their every movement directly, a computer would need memory and processing power to track each atom's state and relationship with all the others at every moment in time. The raw computational demand staggers the imagination. Columbia University physicist Seth Lloyd, in his 2002 paper, Ultimate Physical Limits to Computation, calculated that the entire universe, harnessed as a cosmic computer, could have performed about 10 circumflex 120 operations since the Big Bang. To simulate that, you'd need another universe of comparable size or some mechanism outside our known physics. But simulation theorists reply with a clever twist. Just as in modern games, not everything needs to be simulated all the time, only what an observer interacts with or perceives. This is called on-demand rendering. In a video game, the world is detailed and high resolution directly around the player, while distant scenery is sketched out in fuzzier or more approximate terms, saving on memory and processing. Applied to a simulated universe, this suggests that only those regions being experienced by conscious minds would require the full, atom-by-atom treatment, while everything else could be kept at lower resolution or even generated statistically if and when it's needed. Let's bring in another analogy. Think of movies filmed on elaborate sets. Only the locations where the actors move are built in full detail. Backdrops and side areas are often painted illusions or digitally inserted as needed. Similarly, a simulation could optimize, rendering only the set pieces that fall under direct scrutiny, dynamically updating them when a simulated observer pays attention. But even with these clever optimizations, there remains a monumental computational barrier. Consider human consciousness itself. Your brain hosts some 86 billion neurons, each connected to thousands of others, producing perhaps 100 trillion synaptic connections. Simulating just one functioning brain at a realistic level could require a massive supercomputer. Expanding this to billions of conscious minds, each with rich experience, memory, and intuition, the exponential growth in resource demand intensifies. To address the challenge, some theorists point to Moore's law and the possibility of exotic technologies like quantum computers, machines that exploit quantum mechanics to process information at speeds unfathomable by today's standards. A quantum computer might, in principle, perform instant calculations over vast possibilities, leveraging an effect known as superposition. If an advanced civilization could build quantum computers the size of planets, or our entire solar system, perhaps they could run detailed interactive simulations on a truly cosmic scale. Yet even with such speculative power, practical questions remain. Would the energy required be available? What about cooling the system and maintaining stability across immense timescales? Might shortcuts in simulation produce subtle anomalies, our so-called glitches? Or would a masterful programmer devise ingenious workarounds? These questions sometimes lead to deeper physics, cosmology, and even computer science research as we try to peer behind the veil of our own universe. It's important to note that, to date, there is no direct evidence that such massive hardware exists anywhere, nor can we yet know whether the laws of physics would allow for machines of that magnitude to be constructed by us or by any other beings. As you lie back, imagining these computational behemoths, let your thoughts rest in gentle awe. The scale and sophistication required to render a conscious, interactive universe is breathtaking. And yet, so is the evolution of our own technology, spiraling ever upward. The boundary between the possible and the impossible draws closer with each generation, encouraging us to dream quietly of worlds built not just from atoms, but from the artistry of code and the limitless resource of curiosity. As we continue quietly wondering at the vastness of possibility, let's slip into a truly mind-expanding thought, that our universe might not be singular, but one of countless parallel realities, many branching, interacting, or even themselves simulated. Here, the boundary between what is physical and what is virtual becomes even blurrier. For the multiverse hypothesis and the idea of nested simulations dovetail into a grander tapestry of existence than any one world could hold. First, let's gently explore the multiverse, a concept born from the edges of quantum physics and cosmology. In the 1950s, physicist Hugh Everett III proposed the many worlds interpretation of quantum mechanics. Every event that could happen does happen, but in different parallel branches of reality. When you choose to turn left instead of right, or a particle spins up rather than down, the universe, so the theory goes, splits, forming two diverging but equally real worlds. These countless universes are hypothesized to exist alongside ours, invisible but complete, each carrying out a grand experiment with every possible variation of history and future. Cosmology offers other versions of the multiverse too. Some theories suggest that pocket universes constantly bud off from cosmic inflation, regions where the laws of physics might even differ, separated from each other by horizons forever unbridgeable. In some forms, this infinite branching set of universes multiplies reality to an unimaginable scale, each one as intricate and self-consistent as the last. Now, enter the world of nested simulations. Computer scientists have pointed out that if it is possible to simulate entire universes at a high enough fidelity for consciousness to arise, then there's nothing to stop those within the simulation, if they develop sufficient technology, from running simulations of their own. Each of these would in turn have the potential to spawn further simulations, resulting in a hierarchy or nesting of realities, each unaware of its origin. Think of Russian nesting dolls, each world contained inside a larger one, and those within possibly containing smaller and smaller worlds in turn. Both the parallel universe and nested simulation ideas present a profound shift in perspective. Our universe may not be the bottom layer, or even particularly special. If simulations can exist within simulations, it quickly becomes impossible to know if you're part of the base reality or further down the chain. Some interpretations of the simulation hypothesis embrace this possibility, imagining reality as a branching, fractal-like maze of worlds, each as vivid as your own. This isn't just the stuff of late-night imagination. In theoretical physics, the multiverse helps address certain puzzles, like why the universe's physical constants are so precisely fine-tuned for life. If there are infinite universes, all with different settings, we simply happen to experience one in which conditions allow consciousness to emerge and ask questions about its own origins. Similarly, some simulation theorists suggest that the apparent design of nature's laws could be explained if different simulations are run with different rules, with only a few permitting life to thrive. For computer scientists and philosophers alike, questions of identity, memory, and continuity become ever more poignant in a nested or parallel scheme. Are you the same self in all universes, or do you exist in an endless parade of mirrors and echoes? If a version of you exists in another simulation, do your choices truly matter beyond your current world? These questions are profound but also tender, reassuring us that existence, however structured or multiplied, is a marvel to savor, whether as a singular note in a vast song or a thread in a greater cosmic braid. It's worth pausing to appreciate that while these theories weave wild tapestries of possibility, they remain for now speculative, supported by mathematical models, philosophical logic, and the boundless hunger of human curiosity, but not yet by empirical test. Still, they offer a gentle wonder. Your life, your dreams, and the quiet questions that fill your nights might echo, not just through one universe or simulation, but across a multitude, known and unknown. And so, as you lie quietly, consider the grandness of a reality with space for infinite worlds, each as real in memory and meaning as your own, each quietly humming in the dark perhaps, with its own sleepy scientists, dreaming of what lies beneath. As we linger in this zone of tranquil speculation, the question arises, if reality is a simulation, is it ever possible to escape it, or even to prove once and for all that our universe is not the base reality, but a masterfully crafted replica? This is a question that dances delicately between science fiction and philosophical rigor, and yet it captures one of humanity's deepest impulses, the yearning to pull back the cosmic curtain, to see the true machinery behind experience. Let's first consider the idea of proving our simulated status. Some physicists and computer scientists have long wondered about telltale flaws or evidence that could offer a definitive answer. As we've explored, ideas have blossomed about looking for digital artifacts in nature, a grid-like structure in cosmic rays, minute quantization revealing a finite resolution to the universe, or perhaps irregularities in fundamental constants. Despite the ingenuity behind these approaches, so far, every experiment remains consistent with a seamless, self-consistent universe. If a simulation exists, it appears designed to be virtually undetectable to those within. Beyond physical evidence, some have looked to logical or mathematical paradoxes for clues. For example, Oxford computer scientist David Deutsch once speculated that truly random quantum events or mathematical incompleteness in physical theory might suggest a boundary or limitation that could be interpreted as evidence for simulation. There is the perennial hope, too, that perhaps a message from the simulator, a cosmic Easter egg, some encoded pattern in physics or the digits of pi, might someday be found. Such hopes are poetic but as yet unsupported by science. The notion of escaping a simulation expands quickly from physics into classic philosophy. Here we find echoes of Descartes and his demon or Plato's cave. Can prisoners ever see the sun, or is our role always to interpret shadows? If, for instance, your experiences, perceptions, and even memories are all created within the simulation, then all your reasoning and evidence are enclosed by the rules and boundaries established by the simulation itself. This is sometimes called the epistemic closure problem. Even if you try to leap outside the system, you're still using tools provided by the system. This raises profound questions about the very possibility of transcendence. Science fiction offers imaginative responses. In stories and films, protagonists find secret codes or glitches, hack into the master controls, or are unplugged by forces outside the system. These narratives echo the playful hope that escape is possible through cleverness or revolt, a hope kept alive, perhaps by human creativity and stubbornness. In practical scientific terms, however, since all data is mediated by the simulated reality, detecting the outside is a paradox. Are minds able to reach beyond the code, or is outside contact filtered, like radio signals that never quite reach the receiver or are interpreted only as static by those inside? More constructively, some philosophers argue for pragmatic acceptance. Even if we can never escape or perfectly prove or disprove simulation, our task remains to flourish in the system we inhabit. The meaning of your life, the pursuit of knowledge, the bonds of friendship and love are real for you and those around you, regardless of the system's ultimate nature. In fact, every scientific discovery, every philosophical insight adds richness to the simulation, should there be one, and these achievements become part of its structure. Then there's the idea of levels. If our universe is a simulation and we develop the technology to run simulations of our own, could we establish contact with other levels of reality? Might there be pathways, not out, but between worlds, universes speaking to each other through the codes of their creators? Some have speculated about creating experiments within sophisticated simulated worlds, in the hope that our simulated creations might discover their own status and even communicate up to us. So far, this remains more thought experiment than practical plan, but it's a testament to the unique inventiveness of minds who dream of more. As you nestle deeper into comfort, recognize that this question of escape is, at heart, about our longing for certainty and for understanding our place in the grandest of schemes. Whether or not there's a door in the code, or a message from outside, your powers of inquiry and imagination soar within the bounds of the knowable. In this way, perhaps the boundary is not a wall, but a gentle veil. A challenge not meant to frustrate, but to inspire ever greater curiosity, contentment, and awe. Let's return for a moment from the cosmic scale to the soft, personal realm of your own waking life. Whether or not you ever discover a glitch or find proof of simulation, the question itself quietly shapes how people think, feel, and relate to one another. How does the idea that reality might be simulated touch you, influence your feelings about your day-to-day experience, or alter the way you see yourself and others? The answer, like all good science, lives both in numbers and narratives, in silent transformations of perspective, and in the ethics that follow us into even the smallest moments. First, let's consider the psychological effect. For some, the possibility of living inside a simulation is a source of existential unease. If everything could be virtual, what meaning remains? Yet for many, it is instead a prompt for wonder and resilience. Ancient philosophers like Zhuangzi dreaming he was a butterfly, or Plato contemplating his cave, taught that radical uncertainty doesn't dissolve reality's value. It invites you to savor sensation, insight, and kindness all the more. Knowing that experience is fleeting, even possibly constructed, can make beauty sharper, empathy deeper, and gratitude for the now more acute. A surprising number of people, especially in the age of video games and digital immersion, report thinking about the simulation idea during moments of stress or joy. In 2022, a global survey led by YouGov found that roughly 1 in 4 Americans under age 30 said they found simulation theory somewhat likely, a testament to how vividly the line between digital and physical already blurs in our lives. For some, this is a playful comfort. If reality is a simulation, then perhaps it's possible to reprogram your habits and mindsets, trying on different ways of being with less fear of finality. Visualization techniques, mindfulness practices, and cognitive therapies often work this way, encouraging you to see your thoughts, emotions, and memories as patterns you can observe and, sometimes, gently reshape. Ethically, the simulation hypothesis brings fresh relevance to ancient teachings about treating others with dignity, respect, and compassion. If all experiences are, in some sense, grounded in shared code, if the difference between real or simulated pain, joy, or love becomes functionally meaningless, then the ethical imperative to minimize harm and maximize kindness only grows. Philosopher Nick Bostrom and others have written about this universal empathy, urging us to act as though all beings capable of suffering or joy are equally deserving of care, regardless of their origins. There's also the matter of responsibility. If a simulated world can run multiple times, rewound, replayed, or forked like a saved game, does that change the weight of your decisions? Here, philosophical debates branch with gentle nuance. Some argue that the value of choice is rooted in subjective experience, while others wonder whether repeated or simulated suffering might place new duties on hypothetical creators. For the everyday thinker, this is a gentle reminder to consider the possible echoes of one's actions, whether the world is base reality, a dream, or a carefully coded marvel. On the lighter side, many find that reflecting on simulation theory opens up new avenues for creative thought. It has inspired countless works of science fiction, art, music, and even new kinds of games. Teachers and scientists have used the idea as a framework for discussing probability, statistics, the philosophy of mind, and the intricacies of artificial intelligence. In classrooms and living rooms around the world, the simulation question sparks lively, sometimes hilarious, always profound conversations, each of which adds just a little comfort and curiosity to the shared experience of being alive. Practically speaking, embracing mystery, the sense that you may never know every answer, can bring a special kind of courage. Whether the universe is real, simulated, or something stranger still, you remain an agent of kindness, creativity, and understanding. Your thoughts, feelings, and choices ripple outward, shaping your family, your friendships, and perhaps the simulations and stories yet to come. As you nestle tonight beneath your own ceiling, the science of simulation quietly becomes the art of living well in uncertainty, appreciating the ways your perception is shaped, using curiosity to navigate oddities with wonder instead of fear, and letting the question itself, unsolved and perhaps unsolvable, make life richer, more mindful, and more beautiful with each gentle breath. Draw in a long, slow breath and picture, if you will, the gentle comfort of uncertainty, not as a source of anxiety, but as an invitation to peace, humility, and endless curiosity. The realization that you may never have definitive proof about the fundamental nature of reality is not a flaw in the fabric of science or life. Rather, it is an essential part of the human condition, a tender space where wonder survives and creativity thrives. Scientists are, at heart, explorers of the unknown. Even as they probe the structure of atoms or map the faint afterglow of the Big Bang, they do so knowing with humility that every answer opens new questions. Each layer of understanding uncovers mysteries that are, in their own way, softer, more enveloping, and endlessly beautiful. Whether grappling with the limits of computation, the puzzles of consciousness, or the very possibility of a simulation, physicists, mathematicians, and philosophers all eventually arrive at the edge of certainty, where evidence fades and awe remains. This gentle approach to uncertainty is woven not just into the traditions of Western science, but into the wisdom of cultures around the world. The ancient Taoists of China spoke of the mystery within the mystery, encouraging students to find peace in the unknowable. In Zen, it's said that the mind is most free when it does not rigidly cling to answers, a perspective that resonates beautifully with the open-ended question of simulated reality. The willingness to embrace the unknown, to inhabit the maybe, cultivates a kind of inner spaciousness, a mindful, restful attitude that allows inquiry and acceptance to go hand in hand. On a practical level, comfort in uncertainty allows you to focus on what you can know, shape, and share. Instead of being paralyzed or disheartened by the idea that the universe's ultimate nature might be hidden, you become more present, more anchored in the color of today's sky, the sweetness of a familiar voice, the care embedded in a simple gesture. Paradoxically, realizing that experience itself may be all you're truly granted encourages a deeper, more gentle appreciation of each moment. This orientation also makes you resilient to change and surprise. New discoveries or technological leaps, whether in artificial intelligence, quantum computing, or the next breakthrough in brain science, are less likely to shatter your worldview and more likely to be welcomed, investigated, and woven into the broader tapestry of knowledge and humility. The same applies to your inner weather. Encountering mystery with openness, rather than resistance, fosters adaptability and hope. Even in science, the unknown isn't an enemy to be conquered, but a companion to be cherished, a reminder that our perspective is always partial and there's always more to explore. Some of the most joyful scientific advances have come from unexpected directions, launched by questions that were, at first, outside the boundaries of certainty. That is why even the thought of simulation, sustained by curiosity and not certainty, becomes a gift, an endless wellspring of ideas, experiments, connections, and sometimes wonder-filled rest. So as you snuggle further into sleep, know this: it is perfectly possible and profoundly healthy to rest in mystery, to hold the great questions lightly. Your value, your meaning, your beauty are not diminished by not knowing, but instead grow stronger in your gentle willingness to wonder, to explore, and to dream beyond the edges of even the grandest simulation. Let's rest our minds now on what the future may hold for simulation science, where research, technology, and philosophical thought may gently carry us next. As our computers gain in power, as our understanding of consciousness deepens, and as experimental tools grow ever more exquisite, the boundaries that separate real from simulated, possible from impossible, keep shifting, sometimes inch by inch, sometimes in great illuminating leaps. In laboratories around the world, scientists continue to create ever more sophisticated simulations, both as research tools and as windows into reality's deeper workings. Astrophysicists now model the birth and evolution of galaxies over billions of virtual years, tweaking the rules to test new theories about dark matter or cosmic inflation. In biology, digital evolution software allows researchers to watch virtual organisms adapt, reproduce, and sometimes go extinct within surprisingly lifelike digital environments. These experiments teach us not only about nature, but also about the rules and limits of artificial worlds, and by extension, what it might take for a simulated universe to feel as rich and textured as our own. The field of artificial intelligence, too, is at the heart of this journey. The latest neural networks already mimic aspects of perception and decision-making that were once thought uniquely human. Generative models now write stories, paint pictures, play masterful games, and even converse with us, sometimes so well that they prompt new questions about the nature of agency and creativity. AI agents are increasingly able to roam simulated environments, pursue goals, and develop surprising forms of virtual life. Each advance brings us closer to the day when simulated entities might display behaviors and even self-awareness that rival our own. Then, there are the practical and philosophical quests to test the simulation hypothesis itself. Future experiments may probe even more precisely for pixelation in the structure of space-time, search for subtle breakdowns in physical laws at the finest scales, or uncover patterns of randomness that hint at an underlying programmatic logic. Quantum computers, as they grow more capable, could one day reveal new realms of possibility, enabling simulations so detailed that ethical, social, and technical boundaries will need to be carefully reconsidered. Some visionary scientists even design virtual universes with evolving laws of physics to see if complexity and consciousness might emerge spontaneously right before our eyes. Philosophers, meanwhile, continue to grapple with the deep meaning of these possibilities. The ethics of simulated minds, how to recognize them, value them, and protect them, will only grow more urgent as artificial agents and virtual worlds become more integral to daily life. Debates around free will, identity, and rights may need to be rewritten as simulated beings approach new thresholds of awareness and autonomy. And, as always, there will be the playful, hopeful search for the ultimate clues, a message in the cosmic background, a pattern hidden in fundamental constants, an experimental breakthrough that reveals something about the way our universe is rendered. Whether or not conclusive answers ever emerge, the process will enrich our understanding beyond measure. For you, here and now, the progress of simulation science serves as an invitation, not only to keep learning, but to cultivate that restful, open attitude that welcomes both knowledge and mystery. The future will bring its own surprises, puzzles, and delights. And as you follow along, perhaps joining others in the quiet hours to ponder what really makes a world real, you too help shape the evolving story of science, one that is forever about the gentle interplay of curiosity, humility, and the dream of understanding it all. And so as we come to the end of our gentle journey together tonight, let us quietly reflect on all that we have explored, and the restful wonder with which we can now greet the universe, whatever its underlying nature may be. Whether reality is base, simulated, or something in between, what's clear is that the quest for understanding, undertaken in the quiet dark of night or in the bright halls of science, remains one of humanity's most beautiful pursuits. Throughout this voyage, we have wandered ancient caves with philosophers, walked beside physicists as they measured the cosmos, and listened in on the quiet calculations of neuroscientists and coders as they crafted entire worlds from math and memory. We have learned that our senses always render a model, softening reality into something manageable and meaningful. Computing power has grown from blinking lights to unfathomable speed, making it possible for children and scientists alike to build small universes in a span of hours or days. We have seen, through quantum riddles and the pixel-like whispers of digital physics, how our very laws of nature sometimes seem written with an elegance and efficiency that echoes code. We have pondered the puzzles of probability, the hunt for glitches, and the notion that, fundamentally, information might be the deepest currency of all. We have explored the ethical and philosophical implications for your sense of self, your capacity for love, your exercise of free will, and the meaning that gently arises from every experience, real or simulated. Along the way, we peeked into dazzling futures where artificial intelligence, virtual reality, and ever bolder scientific experiments mean we must always balance our excitement for discovery with humility, compassion, and rest. And in the final stretch, as dreams draw near, we recognize that comfort lies not in certainty, but in wonder, that the universe's mystery is a gentle companion, not an adversary. The boundaries between the real and unreal become softer, not sharper, as you realize that experience, meaning, and care are the constants you carry with you. Even if our world were just a simulation, you would still possess the beauty of curiosity and the power to bring warmth to every moment you inhabit. I'd still love to know where in the world you're watching from and what time it is there, as it's a quiet delight to imagine other sleepy scientists tucked in everywhere beneath this same mysterious sky. May you find peace tonight, feeling the connection between your own thoughts and the incredible web of science, stories, and gentle uncertainty that we all share. May questions softly spiral through your dreams, not to disturb, but to soothe you with the knowledge that being a seeker is its own kind of rest. And now from this peaceful place between speculation and science, between waking and sleep, may your mind be carried forward, out past the edge of thought and softly, ever so softly, into the universe of dreams.